So because most of the parameters for EEG are calculated according to the frequency bands, the first step in any analysis is to determine the EEG frequency spectrum, and usually in accordance with that, the EEG power in each frequency band. So like any other field, the frequency spectrum in EEG analysis is found through the Fourier transform. So let's talk a little bit about that. The problem with just taking a Fourier transform and finding the distribution in frequency space, there are a couple of problems. First of all, EEG is not a stationary signal. So remember that typically when we use Fourier analysis, we always make this assumption that we have a linear system that is stationary, so it's linear, time invariant. So in fact, the EEG is not time invariant because it's a non-stationary signal, particularly if you're looking at evoked potentials or task-oriented EEG. There can be significant changes in the time domain of your spectrum. So that's the first issue. The second issue is that EEG is sort of a stochastic signal. It sort of has obeys probabilistic models, but it's also sort of deterministic and has some nonlinear aspects to it. So the second issue with the Fourier transform is that the EEG is probably deterministic. It probably is nonlinear. We can make some assumptions that it is linear and it is stochastic, but we usually cannot make assumptions that it is stationary unless we're just looking at resting state EEG. So the other issue is that EEG recordings are time limited. So normally when we would do a Fourier analysis and look at a frequency domain, you usually make an assumption that the signal is infinite in duration. So the problem with a time-limited signal is that you have a clear starting and stopping point outside of which the signal has a value of 0. And so what this really means that you've done is you've taken your data set in the time domain and multiplied that by a rectangular window and given it a clear starting and stopping point. And so you may remember from linear systems that multiplication in the time domain is convolution in the frequency domain. What this means is when you determine the frequency spectrum of a limited recording, EEG recording of actual data, your spectrum will actually be the convolution of the spectrum of the data and the spectrum of the rectangular window. So often, to get around this problem, before the Fourier transform is taken, before anything is done in the frequency domain, often the EEG recording will be multiplied by a different kind of window, something like a Chebyshev window or a Hamming window or some window of a different shape that is less likely to superimpose a drastically different frequency characteristic on your data. So a lot of times when you're processing EEG data and you go back and look at your data, you find that the values of the EEG at the beginning and end of the data set are very close to 0. And that is usually because most computer programs like MATLAB, once you apply a filter, they have also applied as a default this Hamming window. So once the data are filtered in the pre-processing stage, you often will look at your first few data values in your data set and see that they're equal to 0. Okay, so because of this, because of all of these issues, a lot of times what's done is you don't just take your entire EEG data set, do a Fourier transform, and represent that in the frequency domain. Instead, you use some sort of tool known as spectral estimation. So there are lots of ways to do spectral estimation. Your standard FFT, there are a couple of issues. We've referred to some. Another issue is if you look at a standard FFT of EEG data, you find that there's a lot of noise in the spectrum. So the spectrum looks as noisy and trashy as the raw EEG signal. So of course it's very hard to tell any kind of characteristic state, any kind of characteristic shape, because you have these noisy FFTs. So there are a couple of methods that people use to smooth the spectrum. The first and most commonly used is called the Welch method. So what the Welch method does is, instead of analyzing your entire data set, it takes a limited window of data. It takes that limited window of data, calculates the spectrum, and then takes the next window of data, usually with an overlap between windows. So this does a couple of things. First of all, it averages the spectrum for each window, which gives you a smoothing effect. The other thing it does is it uses overlapping of the windows. That minimizes the effects of the edges. Normally, if you picked a segment of your data and you didn't, for your next window, you didn't overlap the segments, you would find that the data on the edges of the window is zeroed out because of this windowing effect that we talked about previously. So that's a problem. So window overlapping is used to minimize those edge effects. The other technique, which we won't talk about in depth, but which is also done not as commonly as the Welch method because it is a little more complicated, is to use something called spectral modeling. And there are a couple of different ways to do this. One can use parametric modeling. One can use non-parametric modeling. But basically, both of these methods use techniques, and the goal is to model the signal and then determine the spectrum of the modeled signal as opposed to determining the spectrum of the real signal. And so you would ask, well, why in the world would you want to do that? Because aren't real data always more accurate than model data? And the answer is yes, if the real data did not have these limitations that we've discussed in the past. So sometimes a person gets a smoother spectrum that's more characteristic of the signal if spectral modeling is used. Okay, so once all of this is done, one is ready to begin to calculate some of the parameters of the EEG. And the first and most common one that's calculated is EEG power. And there are two ways to talk about EEG power. One is absolute power. In absolute power, the EEG signal is typically windowed and filtered for each band, each relevant frequency band, and then the power is determined for each band at each probe location. And it's just a determination of power. Relative power, the EEG power at each probe location is divided in each band is divided by the total power at that location. So what a person would do here, if you wanted to find the power, the relative power in the beta band, you would filter the EEG signal so that you only have beta. You would find the power of that. You would divide that by the total power for the same probe at the same location. Now, to complicate this, is sometimes people use these terms differently than what we've defined them here. So it's really important when people mention a publication that they calculated the relative power, it's really important to find out exactly how they calculated relative power, because sometimes people mean different things. Absolute power is good if you're trying to find distribution across a number of probes within the brain. So if you really think that a lot of your power in your beta band is concentrated in your frontal lobe, then you could see those kinds of distributions from absolute power. With relative power, remember, you're dividing the power at the location by the total power at the location. So what this is just going to show you is relative beta might be stronger in some locations than others. May or may not be physically significant, just depends on what you're trying to find out from your data. So here is just a little schematic reminding you once again of what the relevant frequency ranges are. Before the power is calculated, filtering operation is done to get your data into a certain frequency band, and then usually the RMS average power is it's the RMS that's typically calculated, and otherwise we would end up with 0, obviously. So the RMS power is calculated, and it's calculated for each band. So that would be our average power feature.